Why Go for microservices? Or why Golang for microservices? First of all, hello. My name is Charlie. I'm a platform engineer at Monzo Bank, which technically makes me a banker, but I try not to think about that. What I am is an engineer, and I was asked to do this talk, or I was asked to do a talk, and I thought, great, I'll talk about the platform, I'll talk about Kubernetes and AWS and everything else. And then somebody at Monzo said, we have too many talks about the platform. Can we talk about something else, please? And I decided to not talk.
Sorry, it's just when I dropped it.
Oh, I dropped it. Okay. Is that better? So, I decided to, this being a Golang meetup, what is it about Golang that most interests me as a platform engineer? And so, I thought, do the languages we use to build systems matter? Does it matter if we use Golang, or does it matter if we use Java, or Python, or anything else? And first of all, because we're talking about microservices, let's try and define what that is. And it's kind of easier to define what a microservice is by what a microservice is not. So, monoliths. Monoliths are functionally distant aspects that are all woven together. So, it's a very common thing to start developing a product, and then you end up with all of your different components that do different things in the same process, running as on the same hardware, on the same computer. Usually you've got components that are tightly coupled together and they're part of the same program. And that has a bunch of advantages. It means that using any component is an in-process call. Like if I want to use the component that formats the name on a credit card, it's part of my process, I can just call it. If I want to share data between components, it's easy, especially big data. If I have a big data blob of something, I can just give the component a pointer to that data blob and it'll work. And I can test my program if I need to without having to run some sort of integration test on the whole system. So there are some advantages to monoliths, but there are some disadvantages. The code base becomes very complex. So when you have a very big application, you have lots and lots and lots of components all in the same program. If you end up with multiple teams, you get very easy conflicts arising when somebody wants to make changes to one part or another part, and you end up with merge conflict hell, and you have to spend time doing pull requests and everything else. And when you want to change a single thing, you have to redeploy your entire application. So, what's an alternative? Let's talk about microservices. Microservices, they're components as individual services. So I may have a component that just works out what the name of a customer should be on a credit card, and its own service. That's the only thing it does. Each component ideally does only one thing. And I use the word ideally like an ideal gas, rather than saying this is what you should do. So I'm talking about an ideal microservice architecture. You need to have simple inter-service communication, so HTTP REST, and components are loosely coupled. So changing one component doesn't really affect another component if they have the same interface. And if that sounds familiar, going back to history, that sounds very like the Unix philosophy. Write programs that do one thing and do them well. Write programs to work together, and write programs that handle text streams, because that is a universal interface. So if you're using Unix and you do an ls and a pipe to grep to a pipe to something else, that's actually a microservice model. It just happens to be one from the 60s. So there are a bunch of advantages. Suddenly, your components are independently deployable. You can deploy the service that changes the name on a customer's card without deploying a service that does something more fundamental or might be more complex to do. You can scale your components independently. If a part of your stack needs to deal with more load than another part of your stack, you don't have to scale every big box, you just scale that particular service. It's much easier to understand your individual components. It means that a team that knows the name change on a credit card, they know that very well, and they might not know the rest of the service, but they don't need to. And it's a natural fit for containerization. When you've got tiny individually deployable components, it's a lot easier to think about sticking them in a Docker image, for example, or running them on a container platform. And all of that put together means that it's a lot easier to take advantage of horizontally scalable systems. If you have a lot of computers, but maybe they're not very big, that's okay, because all of your services are small, and you can run lots of copies across all those different computers. However, all is not rosy. There are a whole bunch of disadvantages to microservices. Suddenly you have much more network I/O in the whole system. So whereas before the call to your name changer service was in your same process and you just called it, now that's actually a network call over the wire. Deeply nested call chains are slow. So if your service A calls service B, which calls service C, which calls service D, each of those is a network call, and each of those are slower than it would be in process. Transferring large payloads is super expensive. If you want to give a service a megabyte of information, you have to send it a megabyte of information. It has to unmarshal that, copy it, maybe send it on somewhere else. It's really hard to do. It becomes harder to understand the whole system as a whole, and it requires much more sophisticated DevOps. And there are more disadvantages. With a big system, suddenly you need things like service discovery. If I want to find the service that's responsible for changing the name on a customer's card, I need to have some way of looking it up, like whether that's DNS or something else. Global transactions are hard to implement. When an action can touch lots and lots of services, how do you wrap that in a transaction? It's really hard. You may need distributed locking. You may need to start a lock at some point in your system and then release it at some other time. And then you've got, as the last point points out, all of your problems suddenly become distributed computing problems. And they're not easy. Before I talk about why Golang is a good fit for this, I'm going to briefly talk about the Monzo platform, which lets me get my fix of talking about Kubernetes and everything else, but in the context of Golang. And your software has to run somewhere. So we could talk about Golang in the abstract, but it's a lot easier to talk about Golang running on something. And Monzo's platform has all of these components. I'll talk about each one of these very briefly. Our container platform is Kubernetes. So Monzo service is roughly 600 individual containers running on 300 nodes inside AWS. And each one of those components might be made up of up to 3 or 6 or 9 units that all do the same job. So we have horizontal scalability for each service. And all of this runs in AWS, and we use a bunch of other stuff for other things. Our infrastructure is 2 physical data centers to connect to the MasterCard network. Effectively, MasterCard gave us or sold us 2 huge boxes, and they're the only things that are allowed to talk to MasterCard, and that's the only reason we have data centers. We'd love to get rid of them, but we can't. And 350 EC2 machines in AWS, which run the container platform in our database stack. And underneath that, we have Cassandra as our underlying state layer. Our container platform uses multi-master Kubernetes and our own extensions to etcd. etcd is a distributed locking system that we've spent some time making a lot more reliable under failure conditions. etcd underpins our entire service. When you're running Kubernetes, etcd is the component that if it dies, you are catastrophically broken. Make sure that you keep etcd up to date. We have different instance types for different workloads. What that means is in AWS we run different sizes of instances. Most of our instances are quite small, but we have a few for services that require lots of memory. I mentioned service discovery before, and we use a product called Linkerd to find all of our components inside Kubernetes and to do things like retrying network calls that go wrong. So when you make a call from service A to service B, if something happens to service B, and the call that you made was a simple HTTP GET, that's always retryable. So Linkerd will handle retrying that for us. All that out the way, right? We can talk about Golang. What Golang features do I actually care about as a platform engineer for building a system, a distributed microservices system? Goroutines. So part of the Go runtime, a goroutine is a function executing concurrently with other goroutines in the same address space. That's wordy, but what it means is multiple functions that might all do different things, and they're scheduled at the same time. They're extremely lightweight, and under the covers, they're multiplexed onto multiple OS threads. So if I fire off 100 goroutines, but I only have 10 real threads, the Go runtime will take care of scheduling those onto the 10 threads and run them all to completion. You can invoke any function as a goroutine. So if you have a function already, it's very easy to invoke it concurrently. including functional literals. So that means you can define functions in line. And don't worry, there's going to be code examples immediately after this. Function literals are closures. And what that means is if you have a variable and before you declare the Go function, it will inherit that copy of that variable. And whenever a Goroutine is blocked, so if you're waiting on I/O or something else, the Go runtime will suspend that Goroutine and start another one. So the Go runtime will always start other Goroutines that are not blocked. So it takes care of the concurrency problem of making sure that things still run. You end up not doing nothing. So here we have a Goroutine example, which was the simplest one I could think of, where we have a function called sleep then hello, and all sleep then hello does is sleeps, and then it says hello. And so in our main, almost fell off stage, in our main function here, we print going hello, and then we say go, which invokes the Goroutine. It tells it just go and do that, and continue processing. We print sleeping 10, sleep for 10 seconds, then finished. On the left we can say going hello, sleeping 10, so we get the print before this happened, and then the function eventually gets scheduled, and it waits for 5 seconds, prints hello, and then because we've waited for 10 seconds here, the last thing we do is we print finish. So that's a Goroutine. I've mentioned that we can have function literals inside a Go program. So here is more or less the same program. We have the main function that prints going hello, and we have a message saying hello friends, and then we have this thing called gofunc. So gofunc is an anonymous function that does this job. It says message becomes equal to message, and that's a closure. What it means is inside this scope, as far as this scope is concerned, message is that copy of this message. We sleep for 5 seconds again and we print a message. So we scheduled this function by saying gofunc, and then we change message to bye friends, and we do the print. Now, what we get over here is going hello, bye friends, sleeping 10, bye friends, finished. But that doesn't actually feel like that's what we wanted. Because when we declared the function here, message becomes equal to message. Like, I think the assumption was, since I wrote this, I know what the assumption is. The assumption was that this would inherit hello friends and not be bye friends. So it's important to note here that when you schedule a Goroutine with Go, the runtime is in charge of when that actually starts. It doesn't start until some point in the future when the Go runtime decides to start it. So what's happened here is, before this function has started, we've already updated message to be bye friends. And therefore, when we hit message becomes equal to message, the value of message is bye friends. That's not great. So when we invoke a function, you can pass it parameters. So a function is just a regular function. I said you can go any function. So here, we go a func, and we pass it a parameter called message. And then at the invocation time of the go func, this will inherit hello friends. And we see going hello, bye friends, sleeping, hello friends, finished. I said that Goroutines are lightweight, and I can make 100,000 of them, and it won't even blink. So my function doesn't do very much. I mean, all it's going to do is print the number that I passed it to and then sleep for 10 seconds. But if I run time for this program, it takes 11 seconds and it doesn't stress the system. It doesn't run 100,000 invocations at once. It will just schedule them to be run by the number of underlying OS threads. And it means that when you're writing Goroutines, you often don't have to worry in the same way that you would worry in some other concurrency language. I don't have to worry about it the same way I would if I was writing Python async or Java threads or anything else. I can fairly safely spawn 100,000 Goroutines and be quite confident that everything will be okay. Channels. So, if we have lots of Goroutines running, a classical problem is how do these concurrent functions communicate, either with the main thread or with each other? And Go provides something called channels, which are typed conduits which you can send and receive messages with an operator. And they're an easy and safe way to coordinate Goroutines. So my Goroutine can talk to the main thread or another Goroutine by sending a message on this pipe. And going back to the Unix paradigm again, channels are like pipes. So if I do ls pipe grep, the output of ls is getting piped to grep in the same way that a Go channel is coordinating my goroutines. We've got an example. So here, our main function here is making a channel of integers. So this is a structure that can accept integers. And the comma 4 here says that it can accept up to 4 integers at a time. So it's a buffer channel. You can write to it 4 times before it will block. And then we've got 100 goroutines that all attempt to write to the messages channel at the same time. And we've kind of scheduled them at the same time. And here in our main loop, we are parsing, we're reading from this channel and then sleeping for a second. So we have one consumer and 100 goroutines trying to write into this channel. And we run this program. What happens is 4 of the goroutines get to write and then they exit. And then all the rest of the goroutines block. They block on messages, send I to messages, because there's no more capacity in the buffer channel until this routine sums them and then finally frees up the channel to have more messages put into it. Go has very good core synchronous primitives. If you've used other languages and you wanted a singleton, you wanted something to happen exactly once, that's very difficult to do in a concurrent system. There is a sync primitive called once, where you declare that you only ever want one copy of this function to ever be run. You have wait groups, which are a simple way to block until all of your goroutines contained within them are finished. And that's super common. And then lower level than that, we have mutexes. So when multiple concurrent goroutines want to access the same resource in Go, that's unsafe. So if you have a map and you have multiple goroutines wanting to read or write to that map, you can't just simply let them read or write from that map, you'll get a crash. And so we have the option of using mutexes, effectively locking a map, reading from it, unlocking a map. The idiomatic way to do that kind of stuff, though, is to use channels and have something else manage your map. And here we have an example of wait groups. So my previous examples all had time.sleep10 at the end, just to wait until everything had finished. But that's really inelegant. So here we spawn 100 goroutines, but this time we're declaring the structure called sync.waitGroup, and whenever we spawn a goroutine, we're adding 1 to the wait group. And then inside the goroutine, we defer a function to say waitGroup.done. So when this function has finished after the time.sleep, this waitGroup.done will trigger, and it will effectively decrement the wait group by 1. And then after we've triggered off our goroutines, we just have to wait for the wait group to finish, and then we exit. And so we have here 100 goroutines, and this time we don't have to wait for 10 seconds to make sure that everything is finished. We just do the time, and it took 0.007 seconds. The computer didn't even notice. Contexts. So when you have a distributed system, particularly one with lots and lots of small components, and you might need to have chains of calls. So my service to do something, it needs to call another service. That service has to call another service, and so on. There should be some way to know that call chain should not continue. Maybe it took too long, or maybe some other event happened that meant that the work that entire system was doing should stop. And the way that Go does this is via contexts. So contexts are across API and cross-process signals. When we have multiple microservices all running as individual components in their own processes, whenever we make a request from one to the other, we should pass them a context. And whenever those services make a request to something else, they should forward on that context. And this means that the parent, the originating service, is free to do things like say, I want to abort if this entire chain takes more than a second. I'm not interested in the result. And we want to avoid any of the computation that would happen if the original process did abort after a second, but there was still work that every other part of the system was still doing. And we do this with contexts. Here, This was the simplest example I could think of for a context. We have a function called worker, and worker takes a context and it takes a message. And its only job is to check to see whether the context is done, and if the context is done, it's going to error. But if it's not done, it's going to print the message. So it's either going to print something or error. And in our main function, we declare that we want a context based on the background context. That's the parent context that your program starts with, and it says with a deadline of 2 seconds. So this context is saying that I only want this to ever take up to 2 seconds, and if it's more than 2 seconds, we should probably abort. And then we call worker with the context hello, which prints hello the first time, and we wait for 5 seconds, so the context has expired, and then we call again with the context, and this time, in the select block, the worker knows that actually it should abort because it's taking too long, but the context has finished, and so the worker prints out context deadline. What other things are important that Golang brings for me as a platform engineer? It brings opinionated formatting using Go format. That sounds like a small thing, it's not. If you've got 30 or 40 teams and they're all developing and they all have their own particular style, it's really difficult to read somebody else's code. Go FMT formats the code the same every time. It has a diagnostic tool called Go Vet, which detects race conditions and common mistakes. As a beginner Go programmer, that's super useful. It has cross-platform compilation support. So I could compile a binary on my MacBook that will run on a Linux host or a Windows host. And key to me is it compiles static binaries with these. So a static binary is an executable that has all of the libraries that it uses compiled directly into the executable. It doesn't use shared libs or call out to the DLL loaders or anything else. Golang has a really sophisticated garbage collector. The garbage collector minimizes stop the world events. So Golang's garbage collector is a mark and sweep garbage collector. It scans everything concurrently with your code, and it attempts to find objects that things may not have a reference to anymore. And then after it's built up a sufficient number of objects that it should look at, it stops the world for under 10 milliseconds, finds all the objects, works out if there's anything that can expire, and then kills them. So we see much less garbage collection, many less garbage collection events that stop processes running in our system. And it has extensive diagnostic tools that you can perform on live production services. If you build them into your services, you can you can ask your service to tell you everything that happened to it in the last time window and get call graphs and everything else. And I'm going to attempt a live demo. And let's build a small, fully concurrent HTTP service and see what that's like. So this looks a lot smaller on my screen, but this is the HTTP service that I want to build. And this is an HTTP service that is going to insult all of us as quickly as it can, or as concurrently as it can. And we have here, I've collapsed some stuff, but principles, adjectives, and actions are just lists of bad words. And we have a function called choose that's going to pick an item from a list that you give it. Then we have this function called geninsult, and this is us pretending to go to the database or do something slow. So geninsult sleeps for a second, and then it formats the string that's going to be full of bad words. We have func insult handler. Now this is the thing that actually services our HTTP request, and it's going to call geninsult and then return us the string. And finally, our main program, all that it does is it initializes the random seed for no reason anymore. I think previously geninsult waited a random time. So we do something useless, and then we register the insult handler on the /insult endpoint. And we should be able to build this. Ideally, we should be able to build this as a Docker image, which is what I really want to show you. So if I do cat file, here we've got a Docker file that's going to build our server. And the way that we're going to build it is using Docker's intermediately build containers. What's going to happen when we do Docker build is it's going to compile our program using static compilation, and then after it's compiled it, we're going to start a new container, a new image. From scratch is the basic Docker image with nothing in it. And then we're going to copy our static binary into that image. So we should end up with an image that has nothing in it apart from the binary. It doesn't have a shell, it doesn't have anything else. So there's nothing to attack inside that image, and it's going to be very, very small. So here we're going to build it, and then we're going to download 50 megabytes of stuff. That's pretty big. Just to build, 105, ouch, to build our executable. It shouldn't take too long. I'm glad the Wi-Fi is not here. Yes, so we compile our program, and then we see that this is the compilation, run GCO enabled 0. So we're building our insult server, and then finally after that's all finished, step 7 of 9 from scratch. So we're making a new image, the scratch image, and we're copying that static binary into that image. And then we should have built something called insult server. Latest, brilliant. Let's find out how big that is. For some reason my T button does not work. Hey, so we built an image. So insult server is a Docker image, and it is 6.1 megabytes. So this is a fully featured concurrent HTTP server where the image is only 6 megabytes. Let's run it. Awesome. That did nothing, but we should be able to get some sort of insult out of this, hopefully. My entire talk has been a drive up to me and something. So. Yay! So, and with that, I am done. And I'll take any questions. Actually, wait, no, I have another slide. I totally forgot, I have another slide. Yeah, so let's recap. So my entire talk could have been wrapped up in this slide. Why Golang? Golang lets you write high-performance concurrent components in a straightforward way. I don't have to worry too much about goroutines that might consume a bunch of CPU versus ones that block, because the Go runtime will take care of that for me. It produces small static binaries which run with modest resource allocations. We probably could have run that HTTP server a few thousand times on my computer. It's a great fit for microservice architectures in general, and for containerized workloads in particular, because the Docker images are so tiny. It means that if you have 300 or 400 instances, all of them running Docker, by saving, 100 megabytes for that image versus a JVM-based image, we are saving 100 megabytes times 300 instances in cost for I/O storage and IOPS that we have to provision. And this is why, as a platform engineer, I love Golang. And that's what.